All right. Hello, students. This is Mr. Rich, and this is our first week in This Week in AP Calculus. And what I want to do this week is I want to give an introduction to limits. The very first topic that you're going to study in AP Calculus this year is going to be the idea of a limit. You'll probably spend 2 or 3 weeks on this topic, and then from there you'll move into really your first calculus topic of derivatives. In our school district, we're starting school next week. So we are 1 week out from the start of AP Calculus. So I'll be doing limits for a couple more weeks here on my Sunday show. I had to do today's on Monday instead of Sunday, but normally at 8 o'clock on Sundays is when I'm going to do a summary of what we covered in our AP Calculus class for that week. So my intent here is to give you an overview of what in the world a limit is and why we use them. I'm not going to go too much in depth on how to evaluate limits analytically. I'm going to explain things in the context of something that you already know, which is function notation. And you've been doing and using function notation in your algebra class and your precalc class for a couple of years. It's something that you're very familiar with. And I'm going to try to make a connection from that into what limits are. And then also I'll end tonight with showing you one of the main uses of limits in calculus, and that is using limits to define mathematically what it means for a function to be continuous at a particular x value. So what I'm going to do is I'm going to share my screen with you. So let's do that. And here we go. All right. So I want to start off by taking a look at this function here. Let's do it this way. Here we go. So what I've got here is I have an f of x function. And what I'm asking you here is, what is f of -5, right? This is what we call function notation. And it's something that you're familiar with, right? Because this is asking you something very specific. This is saying that when x takes on this particular value, in other words, when x is exactly -5, what is y exactly equal to? So you know then to go on your function here to go over to -5, which would be right here, and go down and then see what the y value is, and you can see that it's -2. Okay, pretty straightforward. Now, what about f of 3? So for f of 3, I'm going to go to where x is 3, and I'm going to go up and I'm going to attempt to read a y value. But unfortunately, there is a hole right there. There is a void. And so the function really does not exist at 3. So I'm going to say, and I'm going to use the abbreviation DNE. If you haven't seen that before, you will see it a lot in your AP Calculus class. So we're saying that the function, when x takes on a value of 3, exactly 3, the function does not exist. Now, keep in mind what this void is telling you as well is that even though the function does not exist at 3, when x is 3, if I were to ask you what is f of 3.01, the function would exist, right? That void is telling us that it doesn't exist exactly at x equals 3, but just to the right of 3 at 3.01, the function does exist, and it's going to probably be real close to 6. And also the function would exist just to the left of 3. And it also would be probably very, very close to 6. All right. But for our purposes at this point, we're just saying that at exactly x equals 3, the function does not exist. And so we would say DNE. Let's do one more. And let's say that when x takes on a value of 6, what is the y value? So we come over here to where x is equal to 6, and we read our y value, and it is 0. That is what we call function notation. So again, I'm not showing you anything that you don't know at this point since you're going into AP Calculus, but I'm going to make a connection and with this thing that you already know and limits, which you're going to be studying as your first topic in AP Calculus. All right, so a couple of things here that I want to point out to you. Function notation tells us the exact y value of a function when x takes on an exact value. All right, and that was demonstrated by using these three x values here, -5, 3, and 6, and then we looked to see what the y values were for those x values if there indeed was a y value that goes with that x value. All right, now next point I want to make. But it is true that function notation does not tell us what's happening around or very close to the x value in question. And I pointed that out or made a point of that here by saying that while the function f of 3 at x equals 3, the function does not exist. It doesn't have a y value exactly at 3. It doesn't really tell me, this does not in and of itself, minus the graph, right? The graph does give me some extra information. But if I tell you that a function doesn't exist at x equals 3, that doesn't really tell you what's going on very close to 3 at like 3.01 or at 2.99. Because the only thing that function notation tells you is what's happening exactly at x equals 3. Okay. Also, keep in mind, class, you probably learned maybe in your pre-calculus class what are different types of discontinuities, right? This void right here is what we call a discontinuity in the function, because I can draw the function with a one pencil stroke, but when I get to that spot, I have to lift my pencil and jump to the other side of x equals 3 to continue drawing the function. And so that's what we call a discontinuity. It's also called a hole in the function, or also the type of discontinuity would be what we call a removable discontinuity in the function. We call it a removable discontinuity because all that it takes is one dot right there to fill in that void, and I have just removed the discontinuity. Okay, now let's take a look at another point. For a function to exist at an x value, there must be a y value associated with that x value. Very obvious. Also, we know a function can only have one y value that's associated with a given x value. Otherwise, it's not a function. So there can only be a y value associated with one particular x value. Now, I want to talk about what limits are going to tell us. So here is what I want to do. I want to introduce to you, if you haven't seen limits before, I'm going to move this out of the way and going to show you what limit notation looks like. You know what function notation is, but here's what limit notation looks like. So limit notation would be, I'm going to use an abbreviation LIM for the limit. And I am going to specify an x value, just like I specify an x value in function notation in parentheses. But here what I'm going to do is I'm going to say x, and I'm going to put an arrow, and I am going to give it an x value at which I want to evaluate the limit. And I'm going to use, for these purposes here, to start it off, I'm going to say a 6. And then I'm going to write the function that I'm considering. And I want to get an answer over here. Now, that looks a lot different than function notation, but really all that I've done is I've put the letters LIM for limit in front of the function and then specified the particular x value right below the LIM. What am I doing? I'm saying here, the limit is asking the question, as x gets really close to this value from both the right and the left side, what do the y values get close to? Not what is f of 6. We know that that's function notation right here, f of 6. But it's asking a different question. It's saying, okay, what about on either side of 6, like at 6.0001 or 5.999, what are the y values getting very, very close to? And so when we zoom in on this function and we take a look at this, what we're basically saying is the closer and closer that I get to x equals 6 from the right side, and then the closer that I would get to it coming in from the left side, do I approach a single y value? And it's pretty clear that yes, I'm going to get very close to a y value of 0. And so the limit is a 0. The answer to this question, the limit as x approaches 6 of the function f of x, the answer is 0. So you should notice here something that's very similar to function notation is this is a y value. And this obviously, since there's explicitly an x and an arrow, right, that is my x value. So they have that in common, right? But the limit notation and function notation, they give you a y value on the right-hand side, and the x value is over on the left-hand side. Instead of in parentheses, like function notation, when we're dealing with limits, that x value is next to an arrow as x is pointing to it, just to say the limit of f of x as x approaches 6 is 0. All right, now let's do another one. Let's suppose that I want to know what is the limit of my f of x function as x approaches, let's go with negative 5. So what do we do to evaluate that? Well, we do locate negative 5, just like we would if we were using function notation. We would say, okay, here's 5. But let me visualize coming in from the left-hand side and the right-hand side to 5, like coming into negative 5.001 or negative 4.999. What y value do I get closer and closer to? So in other words, if I come in here and the closer I get to a x equals negative 5, I get really, really close to a negative 2. And as I come in from the right-hand side, the closer I get to x equals negative 5 from the right-hand side, the closer and closer and closer I get to negative 2. And so we could say that this is equal to negative 2. All right. Now, that's also kind of similar to saying this. We could say that what this is really telling us is that f of negative 4.9999 is approximately negative 2. Okay, it's getting very close. It's a closer and closer, right? It go to negative 4.99999. An infinite number of nines means I'm getting closer and closer to that negative 2 value. But instead of doing something like this, that is not a good use of function notation. Instead, we use limit notation to express what the y values of the function are the closer and closer that I get to this x value. Now, keep in mind, this isn't telling me, limit notation is not telling me what the y value is when the x value takes on this value. We're talking about as we get close to that x value. And here's, I think, what will drive that point home. Let's talk about, for this particular function, what is the limit as x approaches 3? All right, so let's suppose then that we say, here's the question now. What's the limit of my function f of x as x approaches 3? We already know that the function does not exist at 3. But if we take a look at this function at x equals 3, and we say, gee, if I come in from the right-hand side and get closer and closer and closer to x equals 3, I get closer and closer to 6. And as I come in from the left-hand side and I get closer and closer and closer to x equals 3, I start to get very, very close to 6. And so the limit here is 6. Now, we already established something that's true about function notation, that f of 3 does not exist because the function does not have a y value exactly at 3. But as I said, that doesn't tell the whole story about what's happening around x equals 3, because now we know that the closer that I get to x equals 3 from both the right-hand side and the left-hand side at 3.0001 and 2.9999, the closer I get to 3 from both left and right, the closer I'm getting to an x value, excuse me, the closer I'm getting to a y value of 6. All right, so the limit does exist as x approaches 3, but the function does not exist at x equals 3. So that's what limits are used for. They're used to tell us what the function's doing as I get close to an x value, but not exactly at the x value. Now, let me show you another example of this. Oh, and here's another point that I wanted to make before I move on and show you another example. For a limit to exist as x approaches a value, the y value must be the same from both the left-hand side and the right-hand side. You know, because if you think about it, if you're evaluating a function using function notation at a particular x value, there is no left and right, right? It's just at that particular spot. You're looking at the spot where x is that value, and you're looking for what is the exact y value. But if you're talking about a limit, you have to consider what's happening on either side of that x value, because we're not talking about at the x value, we're talking around it. So around it would mean left and right. So let me show you an example. Suppose we took that function that we were just examining and we erase this portion of the function. All right, we would call this a piecewise function, right? This is a function that is consisting of a linear function, and it looks like perhaps part of a quadratic function. But if I remove this linear function here, and suppose I replace it with a horizontal linear function like this. Now, if I say what's f of 3, we come to exactly x equals 3, and we go up and we see that there's a void here and there's a void here. So the function still does not exist. But what if I decide to take the limit of my function f of x as x approaches 3? This requires me to look on both the right-hand side and left-hand side. Now, the y value that I get closer to as I come into x equals 3 from the right-hand side is 8. I'm going to get closer and closer to y equals 8. Okay, I'm not going to write that there because that's not the answer to this question, as you're about to see. But if I come in from the left-hand side at x equals 3, the closer I get to x equals 3 from the left-hand side, the closer I get to the value of 6. Those values are not the same value. So that means the limit doesn't exist either. And one of the ways that we do, kind of as a way to evaluate a limit such as this in a graphical sense, is I can express what we call a right-handed and a left-handed limit using another alteration to this notation. And here's what I would do. I can say that the limit as x approaches 3 from the right. So I use a superscript, a plus sign superscript, to mean what we call a one-sided limit, meaning in this case, a right-handed limit, as I'm coming into 3 from the right-hand side of my function f of x. Now I can give this a number, and that is 8, because from the right-hand side, I'm getting closer and closer to a y value of 8. I can also then do a left-handed limit, which means I would put a superscript with a minus sign to communicate that I mean coming in from the left-hand side of 3. And if I were to express the answer to this, I would say, well, it's the closer I get to x equals 3 coming in from the left-hand side of my function, it's a different value. It's a y value of 6. And because these two are not the same, because my right-handed limit and my left-hand limit are different, that's what then requires me to say that overall the limit as x approaches 3 does not exist. So the bottom line here that I'm trying to communicate to you is a limit is going to exist as x approaches a particular value if you are converging on the same y value from the left and from the right. Now, think about this too, students. If I were to maybe fill in this dot right here, what would that do? Well, that would then say, well, the function no longer does not exist at 8. The function is 8. At x equals 3, the function is exactly 8 because that's where the dot is. I could not fill in both dots, obviously, because then this would not be a function. I'd have two y values associated with that one x value. But that would change that. Now, would filling in that dot change either of these right and left-handed limits? It would not change it at all, right? Because limits aren't talking about at that particular exact x value anyways. They're talking about what's happening as you get very close to that x value. So that's what that would look like. So the limit here, the limit coming in from the right is 8. Limit coming in from the left is 6. Therefore, the limit does not exist. All right. Now, if we go back up, one other thing before I kind of show you the main application for limits in our calculus class, which is going to be for continuity. Right? If we come back to our original function here, and if we were to fill in this dot, right, we were to remove that discontinuity, well, what's that going to change? That's just going to change the fact that f of 3 is now going to be 6. And it also means that the limit as I approach 3 is still going to be 6. That's not going to change that at all because the limit is not talking about what happens when x is 3, but when we get close to 3. And whether that's filled in or not, that's not going to affect the limit at x equals 3. All right, so now we'll wrap this up kind of by saying, okay, where are we going to use this, right? We're going to use this to define what we call continuity. You probably, in most of your pre-calculus classes, and maybe in algebra 2, you talked about the idea of a function being continuous. Now, generally, when we talk about continuity, we talk about continuity at particular x values of a function. Like I may want to know of this function that we are looking at here. I could ask the question, is the function continuous at x equals -4? And the answer would be yes, because at x equals -4, I can see that it kind of is a smooth curve. It just passes right through and keeps on going. Didn't have to lift my pencil up to continue the function when my pencil got to x equals -4. However, I know that the function was discontinuous, as I said earlier, at x equals 3. Because if I'm drawing the function, I'm going to have to lift my pencil off the paper and move it to the other side of this void to continue drawing my function. So, but that's not a really precise definition of continuity. Do I have to lift my pencil off the paper? Right now, there are other discontinuities that you learned that I'm not going to cover tonight. Like we have infinite discontinuities where we happen to have a vertical asymptote, or we can have jump discontinuities, which is really what this is, right? This right here is called a jump discontinuity. The function comes and terminates here just before this void, but then it jumps up to another y value and then keeps on going. Jump discontinuity. But at any rate, we can use limits to define what it means for a function to be continuous at a particular x value. And this is what you're going to learn in your first unit of AP Calculus AB. And that is the definition of continuity. So I'm going to go ahead and give you this definition here. So for a function f of x to be continuous at a particular x value, and I'm going to use the letter c at x equals c. So some value of x that I am calling c. Three things have to be true. For f of x to be continuous at x equals 3, number one, the limit as x approaches c, the limit of my function f of x as x approaches c must exist. That means then that there has to be, from both the left and the right-hand side, the function must be getting close to a particular y value. All right, so that's the first requirement for a function to be continuous. Number two, f of c must exist. So the function has to exist at that particular x value. Now, notice I've just used function notation and limit notation here in this definition. The limit notation as x approaches c is talking about what the function's doing very, very, very close to c at x equals c at either side. F of c is referring to what is the function doing exactly at x equals c. And then the third requirement is that the third requirement for a function to be continuous at x equals c is that the limit as x approaches c of f of x, it must be equal to whatever that f of c is. So for example, let me show you what I mean by this. And this is our definition for continuity. Okay, and you'll see many different types of problems that will be thrown at you where you'll use this definition of continuity. But let me go back to our original function and we'll close it out with this. So for sure, right? If I ask the question, in fact, I'm going to copy this down and take it to a fresh space here for us to look at. There we go. Now, suppose the question is this. Here is my function f of x. And we are asking this question, is f of x continuous at x equals -5? That is the question. We're going to use the definition of continuity. You could say, yeah, sure, looks like it is because I can see that the function is smooth and continues right on through at x equals -5. But I'm going to apply this three-part definition. So number one, the limit of this function f of x as x approaches -5 is equal to -2. So exists. The limit does exist. All right, number two, does the function exist? What is f of -5? It's equal to -2. So I passed part two. All right, all three of those things that I showed you have to be true for the function to be continuous. And number three, it is true that the limit as x approaches -5, the limit of my function as x approaches -5 is equal to f of -5, like that. Okay, so you can see that if you take a look at this function right here at x equals 3, let's kind of wrap this up at -5. So here at -5, the function exists. It's -2. But also as I come in from the right and from the left and get closer and closer to x equals -5, closer and closer to the same value of -2. Now over here, when we look at x equals 3, what would be failing here? Well, this would be true. The limit does exist at x equals 3, and that limit is 6. However, number 2, it does not pass the second step of the continuity test, because f of 3 does not exist. And so the game is over. It's not continuous. Now, if I fill in that hole right there, if I remove that discontinuity by plugging it right there, then all of a sudden it is continuous, right? We know that it's continuous because I can draw it without lifting my pencil off the paper, but it meets the 3 definitions, the 3-part definition. The limit does exist at 3, it's 6. The function does exist at 3, it's 6. And the limit is equal to the value of the function at that x value, it's continuous. All right, class, I hope that helps. And this is just to kind of give you an idea of what in the world functions are. There's going to be a lot more that you learn about functions, a lot more, because you'll have to be able to evaluate limits analytically without the benefit of looking at the graph of the function. So there's a lot more to it. I just wanted to give you an idea of conceptually what is a limit and why do we use limit notations to help us describe the characteristics of a function. And be sure to join me next week, Sunday at 8 o'clock. I'm going to continue talking about limits. And if you saw some value in this video, if you're still hanging around and you're watching this on the replay, be sure to hit the like button and also subscribe to my channel so you'll get notified when I go live again or push new content out to my YouTube channel. Thanks for stopping in, and I will see you next week.